So there are more things you can do in CellNav other than just finding the line of position of a body. Think of it just like in TNav. You could, uh, when you're sailing coastwise and you can see land and you take measurements of your sites to specific landmarks, that could be for two possible reasons. Either you're getting a line of position so you can find where you are in space, or if, let's say, there's an object with a known bearing, potentially because in that case it would be a range where there are two objects in line with one another. You could then take a bearing of that and use it to measure against your compasses, both your gyro and your magnetic compass, to determine what kind of errors exist in the compass. The same is true in CellNav. You could find your line of position by measuring a body, or you could measure the bearing of an object, whether it be the sun, the stars, planets, whatever they may be, to determine your compass error. And that's actually the most common type of CellNav that people will practically, realistically be using, because finding your position, finding a fix isn't really that important. If we have GPS, we know that 90% of the time we can rely on GPS as long as we know how to work with CellNav. But measuring compass error is something you need an external object for, and if you're not inside of land, you do need to use CellNav for it. That's your only option. So this is actually probably the most practical aspect of CellNav that you could be learning about. So the way an azimuth, the function of an azimuth works is, if you go look back to when we take LOPs of bodies, part of the calculation involves finding ZN. If I open up Pub 229 right now, right there, these Z's here refer to the bearings, the azimuth of the body, whatever that body may be. Meaning, using the same calculations that you normally do to find your line of position, you can calculate what the true bearing of an object will be at any given time. So you can then compare that to what you might physically have taken. Instead of using a sextant in this case, you'd be using a bearing circle, an alidade, whatever it might be, to measure either the sun or the star or whatever you're measuring, and then you'd get that bearing, that gyro bearing, and compare it to the true azimuth that you calculated and find your error between the two. And then from there, you can move on to calculating your magnetic error or whatever you might need to do. Now, it's important to note the calculations here have to be much more precise, because when we're finding a fix through CellNav, the expectation is usually you only need to get within 2 nautical miles to have a fairly accurate fix. So there's a lot of leeway there, whereas that wouldn't do you any good if you had that much leeway when it came to a compass correction. You need it to be really precise. So while the calculations for the azimuth are going to be approximately the same, we're going to be more exacting. So instead of creating an assumed position that's generally in the area that we're working with, we're actually going to use the DR position of the exact time that we took the shot. What that means, though, is that our latitude and our longitude aren't going to come out to be exact values. Our LHA isn't going to be exactly on a degree. It's going to have some remainder there. And that's going to require some additional work later on when we get to Pub 229 to accurately interpolate everything and adjust them to be more precise. So with all of that out of the way, we're going to start with this problem here. And I think for this video, I'm just going to work until we have everything ready for Pub 229. Then I'll have that be a separate video, because that's where the majority of the differences lie. But here's the problem we have. It's 20th of July, and at 1626, we were at this DR position. Now, it's important to note that this is not some previous point that we need to advance to. This is the exact time that we took the shot. You can see right here that the time of the shot was 8:24 chronometer time with 2 minutes of chronometer error. So you'd be coming out to more or less 1626 there. We took a shot of, I forgot to note, but this is the sun. We took a shot of the sun and it was bearing 279.3 degrees. And then it lists us our variation, our gyro heading, our standard heading, and our goal is to find deviation. So once we calculate our true here, we're going to be able to compare it to our gyro bearing and get our gyro error. And then from there, we can work further to eventually calculate what our true or what our deviation is going to be. So just to set things up at the beginning, the process is going to be exactly the same for the first few portions. Let's write zone time, zone description, chronometer time, chronometer error, GMT, just like before. So our zone time is 1626. Our zone description, you can see we're 63 degrees west, so that should come out to be +5, but we should always double check. By 60 plus 63 divided by 15. Yeah, +4. That's why you should double check, because doing it in your head like that might not work. Okay, +4. Then we've got chronometer time. We've got 8:24:18. Chronometer error 0 to 12 slow. So if it's slow, that means we're going to add. So we add the seconds together and we're going to get 30 seconds. Add the minutes, get 26. And then remember, we only focus on this side for chronometer. Then for the hours, we ignore this and we do 4 plus 16 gets us 20, meaning this 8 here was actually 2000, not 800. And there we've got our GMT time. Okay, good. Now that we've done that, we could start working on the GHA section of the problem. So we're going to get hours of the sun. You could also, that's sometimes you write down instead of GHA hours, whatever. Minutes and seconds. Then what's important to note here is instead of writing assumed longitude and calculating that, we're just going to use our DR longitude. And then from there, we'll get our LHA. Then off to the side, we're still going to have the declination, little d, declination again. However, instead of using assumed latitude, we're going to just set our DR latitude. Meaning for those two, we can actually carry it over right now. Our DR latitude is 27 degrees, 13.0 minutes north. And our DR longitude is 063 degrees, 42.0 minutes west. Okay, now we can actually open up the Nautical Almanac and start looking for our information. So firstly, we need to open up to the 20th of July. Okay. July 24th, 20th. Okay. And we're going to come over to the sun. By the way, the differences in azimuths for the different bodies, whether it's an azimuth of the sun or the moon or planets or stars, they're very small. It's not, obviously if it's a star, you're going to have to throw in SHA here to get the LHA, but the complications are not that extreme. And if you know how to get a fix by one of those bodies, you can get an azimuth just as easily. Everything that I go over here is going to be essentially equivalent. You could carry over. Okay. So you'll come down to the 20th here, and we're looking for time 2000. So at 2000, we had a GHA. It's kind of fuzzy, but it says 118.25.8. Okay. And then we have a declination of north 20 degrees, 33.9 minutes. And then we have a little d of 0.5. Ask yourself, we're in, it's July, so it's late July, so it's probably after the solstice. So if we look here at these numbers, we can see, yep, they're going down, meaning that this 0.5 is minus. Now that we've got those pieces of information, we can come to the minutes and seconds. So we come to increments and corrections. We're looking for 26 minutes. Right there, it's just gotta focus. There we go. 26 minutes, we're looking for the sun and planets. And we had 30 seconds. So we come down here, 6 degrees, 37.5 minutes. And then D 0.5 is equal to 0.2. Okay. With that out of the way, we can come back here. And now we just, oh, I missed the smaller GHA here. We're supposed to write in between those two. However, we know we're going to add these two up. And then before we continue with this, west is subtract. However, I do want to draw out the diagram to always make sure. So here we are. If we're in the west, then Greenwich should look something like that. And then the sun has a GHA. I should add them together here just to make it clearer. See, 25.8 plus 37.5 gets us 63.3, so it's 03.3, and we carry the 1. So then we'll do 119 plus 6, 125. So the corrected GHA of the sun is 125 degrees, 33 minutes. Meaning it's further west than we are, so we could put the sun right around there. So if we've got GHA and longitude, then LHA is just GHA minus longitude. Remember, east add, west subtract, but always draw it out. So now we're going to subtract 63 degrees, 42 minutes from 125 degrees, 3.3 minutes. Again, because we're not using an assumed longitude, this is not going to come out to a whole degree value. It's going to come out to something a little more complicated than that. But that is intentional. It's because we're trying to be more precise with everything we do here. So we'll just use the 63.3 minus 42. Gets us 21.3 minutes. And then 124, because we carried the 1 minus 63, will get us 61 degrees. Okay. So there's our LHA, 61 degrees, 21.3 minutes. Now for GHA, we just apply the smaller value, the corrected 0.2 here, and it's subtracting, so north 20 degrees, 33.7 minutes. Okay, so with that, I'll write it off right here. We've got a latitude, 27 degrees, 13.0 minutes north, a declination of north 20 degrees, 33.7 minutes, and an LHA of 061 or 61 degrees, 21.3 minutes. Now, because none of these aren't all whole numbers like they normally are, or they aren't 3 of them whole numbers, it's going to make using Pub 229 a little bit more complicated. We'll get into that in the next video, so this one isn't that long.